Welcome to our second lesson in a series of videos on extractions. In the last video, we focused primarily on some of the fundamental principles that govern the extraction process. In this short video, we're going to look at some of the mechanics behind performing an extraction. So we'll look at some of the glassware for a liquid-liquid extraction, and we'll actually see a simple liquid-liquid extraction take place. Then we're going to show the glassware for a solid liquid extraction, what's often known as a Soxhlet extraction. So first, let's take a look at the liquid-liquid extractions. The flask on your left contains an analyte, some orange chemical dissolved in water. Now, if I want to transfer that chemical from the water to another solution, to another liquid, say what we have here is ethyl acetate, I need to make sure that those two liquids can come into contact with one another. So right now what I'm going to do is just simply pour the ethyl acetate into the water solution. And I'm going to do so very carefully, making sure not to disturb the water layer. And as I do this, you'll notice that the ethyl acetate, which was colorless to begin with, is forming a layer on top of the water layer. Now this shouldn't be too surprising, considering that ethyl acetate and water are not soluble with one another. And furthermore, ethyl acetate is much less dense than water, so it should float to the top. Now as we take a slightly different perspective here, we can see the ethyl acetate layer on the top is still clear. If we wanted to, we could just wait for a while, and eventually that analyte, that orange chemical, would make its way into the ethyl acetate. But we can facilitate this process by agitating. And the more we agitate, the smaller the droplets of each chemical in the opposite phase. And this allows for more surface area interactions and therefore more efficient transfer of the orange chemical from the aqueous phase into the ethyl acetate. Now, once we've finished agitating, the next thing we need to do is simply let it settle out. And you can see that with a little bit of time and a little bit of settling, that the cloudy mixture that was there before is now separated out into two separate phases. Now the ethyl acetate should still be on the top because the ethyl acetate is less dense than water. But notice how the color has changed. Now instead of having the color on the bottom, in the water layer, we now have the color in the top layer, the ethyl acetate. This is because the chemical that was in the water has been extracted from the water phase into the ethyl acetate. Now you may notice that this process of separation and settling out into two layers can take a little while. Sometimes there's an intractable mixture that's formed, what we call an emulsion. There are some tricks to getting around emulsions, but we'll save that for another class. Now the trick here is to be able to separate these two phases now. That way we can separate the chemical of interest from the original phase. Now, one simple strategy to separate those two phases would be to simply decant the top layer off of the bottom layer and into a new flask. While that may work to some extent, it's certainly not the most efficient way of doing so. Instead, when we do an extraction, we use a piece of equipment, a piece of glassware, called a separatory funnel. And the separatory funnel is conical in shape, and it has a stopcock at the bottom. And what this allows us to do is to place our chemical inside of the separatory funnel, allow it to settle out, and then we can drain the bottom layer. And notice that as the line goes down, we will be able to very accurately see the difference between the top layer and the bottom layer. Take a moment to notice the handle on the stopcock. And what you'll see is that that handle can either be oriented in a vertical position or a horizontal position. In the vertical position, the stopcock is open and liquid can drain freely through that port. However, if it's horizontal, it is closed and we don't have to worry about chemicals leaking out. The reason why I mention this is because it's a very, very common mistake for a student to start adding their chemicals to a separatory funnel while the stopcock is still open. So remember, up and down, the stopcock is open. Left to right, the stopcock is closed. Now, as I carefully pour the mixture of liquids into the separatory funnel, notice that I'm careful not to pour anything on the outside of the funnel. Now, during this process, we will be agitating the mixture of liquids through the pouring process, but they are expected to separate out again with a little bit of time. So as you can see already, we're seeing a darker solution at the top and a lighter solution at the bottom. Okay, so in the middle, you'll notice that there's kind of a cloudy layer, something that it looks like there's some kind of a solid precipitate, but it's not. What that is, like I said earlier, it's called an emulsion. And an emulsion is simply a situation where you have some of one layer trapped within another layer. Now, once the two phases are sufficiently separated, we open up the stopcock and start to let the bottom layer flow out of the separatory funnel. We don't want to do this too quickly, because if we do, we risk having some of the upper layer being drawn down into the flask below. So, as we let the liquid flow through the bottom, we notice that the line that marks the interface between the two solvents gets lower and lower as well. And it also becomes through a more constricted part of the glassware, which allows us to very clearly see where the line is between those two phases. Once we've gotten to a point where we have all of the bottom phase emptied out, in other words, no sign of it in the separatory funnel, then we have successfully separated out those two phases. Now, if there's an emulsion of any sort, sometimes you'll still see a little bit of the bottom layer that shows up over time. But if you allow for the bottom layer to separate out with more time, or try some of the tricks that we're going to talk about in a later class, you'll be able to separate those chemicals out completely. But overall, the important thing to take home from this is that we have shown the successful transfer of a single chemical from one solvent to another. Let's take a moment now to look at solid-liquid extractions. There's a couple of things that we need to take note of before we look at the apparatus for a solid-liquid extraction. First, we need to remember that solid-liquid extractions are inherently less efficient than liquid-liquid extractions. And the reason for that being is that it's very difficult to get the two phases to come into contact with one another. In other words, the liquid solvent can only make contact with the solid material on its outer surface. So the larger the particle size, the less capable the solvent will be of removing the desired analyte from that solid material. For this reason, solid-liquid extractions are usually performed in such a way where the particles have been sized very small. This is evident when you look at coffee beans. Nobody brews coffee from coffee beans, but rather they crush the coffee beans first to increase the surface area. The same thing goes for tea, and the same thing goes for any kind of solid-liquid extraction that's performed in a laboratory. One of the tools that's available to us that allows us to do a continuous solid-liquid extraction for long periods of time, and therefore enhancing the efficiency of the process, is called a Soxhlet apparatus. The Soxhlet apparatus is composed of several pieces of equipment. First, we have a round bottom flask at the bottom. Now, typically we're used to seeing the chemical of interest being put into the round bottom flask. But in this case, the round bottom flask will contain the solvent that we're using for this extraction. Connected to the round bottom flask is the actual Soxhlet extractor. Now, I'm not going to talk about this too much just yet, but do notice that there is a little white piece of tubing in there that's actually made out of paper, and that is where you put your sample. And then right above the Soxhlet extractor is a reflux condenser. Now, the way this piece of equipment works is that you attach a water lines to that reflux condenser to allow for water to pass through and cool the condenser. You put your sample inside of the thimble, which is that white piece of paper that is in the middle of the apparatus here. And then we put our solvent in the bottom, in the round bottom flask. At this point, we can heat the bottom flask, and the way we do that is with a heating mantle. And when we warm that up, what's going to happen is that the solvent is going to evaporate, and it's going to make its way up through all the tubes that are inside of the Soxhlet extractor and up into the reflux condenser, where it's going to be cooled down, and then it's going to recondense into the liquid phase. And when it does that, it's going to fall inside of that main chamber where our sample is resting. And that chamber is going to fill up very, very slowly. As it fills up, the solvent will also make its way through this system of tubes on the right-hand side. And once the solvent level hits a certain point, the entire apparatus will recycle the solvent. In other words, the solvent that is inside of the chamber will be completely drained down into the bottom flask again. Now, what's nice about this setup is that the chemicals that make their way to the bottom flask are never going to come into contact with the starting solid that we began with. So this process can take place over and over and over again until we feel that we have sufficiently removed the analyte of interest from our solid sample. In this short video, we have had the opportunity to see first how a liquid-liquid extraction takes place. We were able to see the chemicals literally transfer from one solvent to the next. We were also able to see the types of glassware that we use to carry out a liquid-liquid extraction. And then we moved on to see what it looks like when we run a solid liquid extraction. So you've now formally been introduced to a Soxhlet extraction apparatus. In the laboratory, we're actually going to use this, and you'll have a chance to see it in action. Thank you for watching the video.